Here's a quick revision video on mains electricity. So I'll talk you through it. So mains electricity is anything where you've got to plug it in. So the sockets in your homes, they give out on average 230 volts of potential difference. So it's quite a lot of voltage. So you have to be careful you know what you're doing. So you need to know the difference between AC and DC, how we can measure the current of an appliance, how to wire a plug, and what is the main function of a fuse. Okay, so these are the main objectives from this. Okay, so mains electricity. It's important to know how to use it safely. Okay, so toaster on the right, fridge on the left, they both use mains electricity. The electrical appliances, they both transfer energy. One is for producing heat, the other is for removing heat from inside the fridge and keeping things cool. And they both plug into a 13 amp socket in your home. So the power of an appliance electrically is the rate at which it transforms energy from electricity into other forms. So it's basically a user of electrical work. Okay. Power is measured in watts, which is joules per second, and power is also a measure of work done over time taken, where work done is measured in joules and time is measured in seconds. Those are the SI units used in science. So 1 watt is 1 joule per second. Power and potential difference are printed on most appliances. So the other day I showed my year 11 students how you could determine how much electrical energy was being supplied when you boil some water in a kettle, and we were looking at the thermal energy that can be stored in water. This is something which you'll study in year 11 called the specific capacity of water. And so water can take heat from the kettle and store it as thermal energy inside the water. So all the electricity, it comes from the mains, and the power of the kettle we were using was 2,200 watts, that's 2,200 joules per second, and the potential difference obviously was mains, so it was 230 volts approximately. So once we know the power and the voltage, you can calculate the current, because current is power divided by voltage, or you could say power is voltage times current. Okay. If you put them in a triangle, you can work out, if you have two of them, you can work out the third. So this is good revision for understanding how power, voltage, and current are related. I stands for current, P stands for power, V stands for voltage, and you also need to know the units for each one. So power is watts, voltage is volts, and current is amps or amperes. AC and DC are two types of electricity. Yeah, it's nothing to do with the band AC/DC, which are those of you old enough to remember. I don't know if they're still about. Okay, so it's nothing to do with the rock band. AC stands for alternating current. That means the current is constantly changing. It's a bit like a positive then negative, positive then negative. So it's like a wave in effect, an electrical wave. Direct current is always moving in the same direction, so it's always moving from positive to negative. So in the home we use alternating current, and the energy comes out of one of the pins in the socket, and goes back through the other pin in the socket when you plug in your appliance. Okay, so alternating current means changing current, and direct current means constant current. So cells and batteries are chemical devices, and they supply current that always moves in the same direction. We say it moves from positive to negative. That's our convention for current. So that's conventional current flow is positive to negative, as shown in this diagram. If it's a battery, it will go from positive to negative, and in effect, what's really happening is electrons are going from negative to positive, but the convention is to show it the other way around, okay, in a circuit. If you have a generator, you can produce AC current. So when you have AC, alternating current, is one that's constantly going backwards and forwards and changing direction. So now you see the switch is being moved from the top to the bottom, and the alternating current, you can see the yellow and the grey arrows are constantly changing direction. So it still carries energy, except it doesn't have one direction. As long as the electrons are moving, they're energized by the generator rather than being energized by the chemical process which a battery or a cell provides. Okay, so a battery or a cell uses a chemical energy store to transfer it into an electrical system, and an AC generator uses an electromagnet inside. So an oscilloscope is a device which you may have seen in schools, and it actually is basically a voltmeter, but it can plot voltage against time. So up and down is voltage, and across the x-axis, if you like, is a measure of time. So you can see how the voltage varies against time, and that's what an AC current looks like, or an AC voltage looks like. Okay? You need to be able to interpret and compare oscilloscope graphs for AC and DC supplies. So a DC supply would be a constant voltage against time, it never changes, if it's made from a battery or a cell. And how far up the axis it goes will determine what the voltage is, and you can change the setting on your oscilloscope with those dials. One of them will be the voltage setting, so each square will represent a certain number of volts, so you can read off what the peak voltage is, etc. And you can also work out what's the distance between two peaks, which will tell you the period of the oscillations or the electrical wave that that it represents. And from that you can work out the frequency of an AC wave. So as well as for a DC voltage will be a straight line above the zero. The center of the oscilloscope reads 0 volts. Okay, so going back to the AC wave, up above the center line is positive voltage, and below the center line is negative voltage. So actually the average overall, if you think of it in terms of positive and negative, would be 0 over a whole cycle, but that's not how we measure the voltage of an AC power supply. So there's the DC one, and an AC one goes up and down, and on average over the whole cycle, if you had a DC power supply which could get to 230 volts, the energy supplied by the mains electricity would be as if you had batteries worth 230 volts constantly putting out that amount of energy. Okay, so that's a better way of understanding what 230 volts means. So DC flows in one direction only, directional current you could call it, and potential difference does not change over time, and you can show that on an oscilloscope if you plug in a battery into the inputs for the voltmeter called an oscilloscope. Okay, so it'll be a flat line if you plug it into an oscilloscope. For AC, it will be a wave going up and down above the dotted line in the middle. The dotted line in the middle, as I explained to you, represents 0 volts. So it changes direction over time. In fact, it changes direction 50 times a second, and that's the frequency of mains electricity, which is used in the UK and in the UAE, for those of you taking your IGCSE internationally. Most countries in Europe also use 50 Hertz, and in the US they use 60 Hertz, and that's just the convention that has been set up for those countries. And frequency is measured in hertz, and hertz means cycles per second. Okay, so it's a bit like an electrical wave. So UK mains, as we said, it has 50 cycles per second or 50 hertz, and it's the same in the UAE where I'm teaching. And the potential difference over the whole cycle is as if you had a DC supply of 230 volts. Well, obviously the peak voltage will be higher than 230 volts, and it's beyond the GCSE specification to have to worry about that. Okay, so over here they've drawn 50th of a second between two peaks. That means you get 50 cycles per second, so 50 of those peaked peaks will be 1 second. They've drawn the 230 volts as the peak value, which is incorrect. It will be probably 2/3 of the way up that from the center line. Okay. So it changes direction 50 times a second, and that's what we mean by it. And if the peak potential difference is greater than 230 volts, so I need to correct this slide, but I think I've explained it, so please make sure you realize it's actually the peak voltage will be higher than 230 volts. The 230 volts is, as I said before, it represents what it would be equivalent to having a DC supply of always 230 volts. It would provide the same energy as a DC supply of 230 volts. That's a better way of understanding what it means. So supplying electricity in plugs in your home, you've got the brown wire which has a fuse next to it. That's the live wire. You've got the blue wire which is the neutral wire. So instead of having positive and negative with AC, you've got the brown, which is the live or the energy providing wire, and blue, which is a neutral wire. And basically the power of the electricity is driven by the live wire. So that's kind of where the electricity, the current comes in, and then it flows to the neutral wire, and that's the exit point. The green and yellow wire is a safety wire called the earth wire. You need to know the color coding, yeah? You need to know that the pins that go into the sockets in your wall are made of brass because they're quite strong and they conduct electricity. The casing in the wire cover are insulators to stop you getting an electric shock. So plastic and rubber, and you have a grip there which also makes sure that if you trip over the wire, it doesn't pull the live and wire out by accident. Okay, so you need to know which one's which. Okay, so the earth wire is the green and yellow one, the neutral wire is the blue one, the insulation is anywhere where there is a plastic, the fuse is on the right hand side, it's the cylindrical object, the brown one, next to the brown wire, and the cable grip is the one with the 2 screws in it to hold the cables in place. So when you're wiring a plug, you need to know which one goes where. The brown is always on the right as you're looking at it while you're wiring it. The blue is always on the left. And the green and yellow one is at the top. And the green and yellow one, it only gets used if something goes wrong with the circuit and it needs to defuse the circuit. Literally, it basically sends the current down to earth very suddenly, and that is a safety device. Okay, so live alternates between positive and negative, the live wire, and it can give positive values of up to average of 230 volts in each direction. The neutral is always maintained at a potential difference of 0 volts, which is why it's called the neutral wire. Earth is also connected to, if something has a metal casing, like a kettle that's made of metal, it's a safety path directly from the surface of the metal, of the appliance, which has a metal surface, to the earth for safety. So it's an alternative safety route to earth rather than having to go through the neutral wire. So not all, if the appliance is made of plastic, you probably don't need an earth wire because you can't get an electric shock from it. 2 core cables will be enough for appliances which have plastic casings. Instead, the plug is double insulated with plastic. Okay, so you have plastic everywhere, so we call it double insulation. And plastic, as you know, doesn't conduct electricity, so it's quite safe. If an electric fault is caused and too great a current is created as a result, the fuse blows. The fuse blows when the current gets too high because it can't take more than a specific amount of current, and you can get different fuses for different appliances, and the typical fuse values are 1 amp for the minimum, 3 amps, 5 amps and 13 amps. It is possible to get other ones like 10 amp fuses, but those are the main ones, and you need to know which one you need to fit depending on the power of the appliance. There we have a 3 amp fuse, a 5 amp fuse and a 13 amp fuse, with the symbol for your fuse being a rectangle with a wire going through it, and literally a fuse is a wire, copper wire normally, going through the cylinder inside. Okay, so the fuse is a wire with a low melting point. Well, it has a melting point which relates to the maximum current that it can take. Too much current produces too much heat, and the fuse melts above its rated value if the current is left on for that amount of time. And this breaks the circuit and protects the appliance. And the main job of the fuse is actually to protect the appliance from getting too hot and causing a fire in the house. And of course, it will also prevent electrocution should anyone touch it. But the most important thing is it prevents lots of fires, which is a bigger safety issue than one person getting electrocuted. So if you wanted to investigate fuses, you could actually look at different thicknesses of wire and seeing how much current could be placed through them before they melted. Okay, but they will get very hot, so it is a safety feature, a risk that you need to be aware of if you're doing this. So you need to think about the hypothesis: would a thin wire, for example, or a thick wire be able to take more current? So how would you plan such an investigation? So if you have different standard wire gauges, the bigger the number, the thinner the wire. With SWG, it actually means how many pieces of wire you need to make a certain cable, I think. So that's called the standard wire gauge. So the bigger the number, the thinner it is. In millimeters, you can see that the number inversely relates to the diameter of the wire in millimeters. Okay, so if you've got different thickness wires, you can measure the current in them, and you can see the average current at which the fuse burns out. And you can see the thinnest wire will burn at the lowest current. So you can see the 24 standard wire gauge is the thickest one, and it can take about 5 amps before it melts. So you could do this and see the maximum current that it takes on average based on the wire thickness. Okay, so that's quite a good investigation. I haven't actually done it myself, but the results are interesting to look at. There's the correlation. Okay, so obviously you would analyze it and you could make a conclusion based on what we talked about. And it then says, what thickness fuse would you suggest to use in an appliance designed to run on the following AC currents? Well, if it's designed to run on 1 amp, then you would need to have a fuse value which is higher than 1 amp. And if it's designed to run on 3 amps, you would need to choose a fuse value which is higher than 3 amps. You can't have the same fuse value as the normal operating current, otherwise it will melt while you're operating your device without it being incorrect. So for the 1 amp fuse, for the 1 amp value, current appliance that runs on 1 amp, you should have a 3 amp fuse. For the 3 amp appliance, you would have a 5 amp fuse, and for the 6 amp appliance, you would choose the 13 amp fuse based on the choices I showed you earlier. So you choose the next fuse value up. Okay. There are alternatives. So if you look in your fuse box, they used to be called fuse boxes. They've now replaced them with RCCBs, which are residual current circuit breakers, and these can detect the difference in current between the live, where the current enters, and the neutral. And there shouldn't be a difference. If there is a difference, it switches off, and they basically switch off the current in those circuits where they detect a difference in the current going in to the current coming out. So there's been some leakage of current somewhere in the circuit, so we know there's something wrong, and it will just switch off that circuit. For the exam, you don't need to worry about internally how these RCCBs work, but the good thing about them is you can reset them once you've worked out what the fault was. You don't have to replace them like you would with a fuse. So you need to recap what's the difference between AC and DC. Hopefully you found out what the difference is now, and how can we measure current of an appliance. I think they mean how can we calculate the current of an appliance. To measure it, you'd use an ammeter. I think they mean how do we calculate it. So you need to know the power and the voltage, and if you divide the power by the voltage, you will be able to work out the normal operating current for that device. And how do you wire a plug? Well, obviously you need to know the color coding. Please go back and have a look and make sure you've got notes on all these things. And what is the function of the fuse? Well, I told you the main function of a fuse is to prevent fires. So I hope you found this useful. Yeah. I think that's a good place to stop, and we can do the rest of the video in a future video that I can upload for you. If you found this video useful, please like, share, and subscribe. I'm going to upload it into my YouTube channel for you, and I will see you in the next video. Bye for now.